In this video, we're going to look at some examples where we need to find the interval and radius of convergence for power series. In this first example, we're going to find the interval and radius of convergence of the power series from n equals 0 to infinity of x to the n over n factorial. The main tool in determining the interval and radius of convergence for power series is the ratio test. So we're going to apply the ratio test to this particular power series and use the resulting limit to determine when this power series will converge. So to apply the ratio test here, we need to compute the limit as n approaches infinity of the absolute value of the n plus first term, a sub n plus 1, divided by the nth term, a sub n. So we can substitute in the terms for this particular series. So we have the limit as n goes to infinity. A sub n plus 1 will be x to the n plus 1 divided by n plus 1 factorial. And we're going to divide by a sub n, which is the same thing as multiplying by its reciprocal. So we're going to multiply by n factorial over x to the n. And now we want to simplify the expression inside these absolute value bars and then take the appropriate limit. Notice here that we have n plus 1 factorial, and we know that we can rewrite this as n plus 1 times n factorial. And so our n factorials here will cancel. We also have x to the n plus 1, which we can think of as x to the n times x, and therefore the x to the n's will cancel. And so what we are left with is an x in the numerator, and we're going to have to remember to keep the x in absolute values here because we don't know whether x is going to be positive or negative. Here, x could be a positive or negative number, and so whenever we're dealing with the ratio test and intervals in radii of convergence, we're going to always want to keep expressions of x in absolute value, unless it's something obviously positive, like, for example, x squared. But here we just have a single power of x, which we need to keep in that absolute value. So that's the only term in the numerator. In the denominator, we're left with just n plus 1. And we can leave that outside of the absolute values since we know that n is a positive number and n plus 1 is therefore also positive. So we're computing the limit as n goes to infinity of the absolute value of x over n plus 1. While x is an unknown value, we do know that we're thinking of x as a fixed value, just an unknown value here. And so we have a constant over n plus 1 as the limit of n as n approaches infinity. And this will give us a value of 0, since that denominator will get extremely large as n gets large. And this turns out to not involve the value x at all, the variable x, because 0 is always less than or equal to 1. And so here, we now are able to conclude from the ratio test that regardless of our value of x, our limit of our ratio is always 0, which is less than 1. And therefore, this particular power series converges for all values of x. And when we have such a power series, one that converges for all values of x, we know that the radius of convergence is then an infinite value, so r is going to be infinity. And our interval of convergence, which we'll call I, will be the interval that indicates all real numbers, negative infinity to positive infinity. For our next example, we want to find the interval and radius of convergence of the power series n equals 0 to infinity of n factorial times x to the n. Again, we're going to apply the ratio test here, and so we're going to have the limit as n approaches infinity of the absolute value of the n plus first term, which will be n plus 1 in factorial, times x to the n plus 1, divided by the nth term, which will be n factorial times x to the n, and then we want to compute this limit. So we need to simplify this expression inside our absolute value. We know that n plus 1 factorial we can think of as n plus 1 times n factorial, and therefore our n factorials will cancel, and we're left with just the expression n plus 1. And we can leave that outside of the absolute values since that is going to be a positive number. We also know that x to the n plus 1 can be thought of as x to the n times x, and therefore the x to the n's will cancel, and we'll be left with just a factor of x. And this we need to keep inside absolute values since x could be positive or negative. And so we have the limit as n approaches infinity of n plus 1 times the absolute value of x. Now again, as in the previous example, we don't know what value x is, but we are thinking of it as a fixed constant number. That's the goal, is to determine which values of x work here, but we can think of it as just a fixed but unknown number. And here we're multiplying it by n plus 1, and as we take a limit as n goes to infinity, n plus 1 also goes to infinity. And so this particular limit, as n approaches infinity, we're going to get a constant times a value that gets extremely large, and this will also get extremely large. So this limit will have a value of infinity. It'll be a limit that diverges to positive infinity, and of course, that limit is then greater than 1. So this seems to indicate that our power series never converges. However, we know that power series always converge at their center. And so here, what we have to notice is that this calculation that we computed is only defined when x is not equal to 0. When x is equal to 0, this limit here doesn't make any sense because we're having an x to the n in the denominator, and so we have a 0 denominator here. And so what this calculation is showing is that whenever x is not 0, our series must diverge since we have a limit of the ratio of consecutive terms being greater than 1. And therefore the conclusion is that this converges only at the one value that we know where it will always converge, which is at its center, which is x equal to 0. And so this is a power series that converges only at its center. When we have such a power series, we know that the radius of convergence is equal to 0, and the interval of convergence is the 1 point interval at the center, so the interval from 0 to 0. If you'd like to try an example similar to the previous examples, pause the video and try to find the radius and interval of convergence of the series from n equals 0 to infinity of 3 to the n times x to the n over n factorial. Resume the video and see the full solution in a few seconds. So we apply the ratio test to this particular power series, and we compute the limit as n approaches infinity of the absolute value of 3 to the n plus 1 times x to the n plus 1 over n plus 1 factorial, multiplied by n factorial over 3 to the n times x to the n. When this expression is simplified, we have the limit as n approaches infinity of 3 times the absolute value of x, all divided by n plus 1. As n goes to infinity, the limit of this expression will go to 0, since we have a fixed constant number, 3 times the absolute value of x in the numerator, and our denominator gets large. Since 0 is less than 1, this particular power series will converge for all real numbers, according to the ratio test, and therefore our radius of convergence is infinity, and our interval of convergence is negative infinity to infinity. We now consider some examples of power series where the interval of convergence is not a single point and is not all of the real numbers. In other words, it is some finite interval centering around the center of our power series. In this first example, we want to find the interval and radius of convergence of the series from n equals 0 to infinity of x minus 2 to the n over n plus 1 times 3 to the n. The first thing that we're going to record for future use is that the center of this power series is the number 2. Notice the center is always the value of a, where we have an x minus a to the nth power in our power series, and here we have x minus 2. And so the center would be 2. In order to determine the interval and radius of convergence, we're going to apply the ratio test to this particular power series. So we want to compute the limit as n goes to infinity of the absolute value of the n plus first term, which will be x minus 2 to the n plus 1, over n plus 2, because we're going to replace n with n plus 1, and so that expression in the denominator will be n plus 1, or n plus 2, times 3 to the n plus 1. We're then going to multiply that by the reciprocal of the nth term, which will be n plus 1 times 3 to the n over x minus 2 to the n. And we'd like to compute this particular limit. This means we have to first simplify all of this in the absolute value bars. So notice first for our powers of x, we have n plus 1 factors of x minus 2 in the numerator, and we have n factors in the denominator. So the x minus 2 to the n in the denominator will cancel with almost all of the x minus 2's in the numerator, but we're going to be left with one of them. So we're just simply going to be left with x minus 2 to the first power. And because x could be positive or negative, and that means x minus 2 could be positive or negative, we're going to leave the x minus 2 in the absolute values. We also have 3 to the n. That'll cancel with the 3 to the n in the denominator, and we're going to have 1 3 remaining in that denominator. So we'll have x minus 2 an absolute value over 3. And then we have n plus 1 and n plus 2, which don't simplify in any meaningful way, and so we'll simply multiply this by n plus 1 over n plus 2. And this will be our simplified version. Notice the n plus 1, n plus 2 is outside of the absolute values, since n is positive, and then therefore so are n plus 1 and n plus 2. Now, x minus 2 over 3 is a constant in terms of n, and so we can pull that outside of our limit and compute the limit of just n plus 1 over n plus 2. And this limit is very easy to compute. We can use L'Hopital's rule, for example, or we can multiply both numerator and denominator by 1 over n. And when we do either of those things, what we're going to get is a value of 1 for that limit. And so our resulting overall limit, including the constant that we pulled out front, is the absolute value of x minus 2 divided by 3. And this is what will often happen with interval and radius of convergence problems with power series, is that when we compute this limit with the ratio test, we'll obtain a limit that involves the number x, because that limit will be dependent upon which value of x we're substituting in. And so in this case, this value depends on x. And so this tells us that for some values of x, we're going to get a convergent series. And for other values of x, we're going to get a divergent series. Since we're applying the ratio test here, we know that our series will converge whenever our limit that we just computed is less than 1. And so our power series will be a convergent power series when the absolute value of x minus 2 over 3 is less than 1. We can then solve this inequality for x to find our interval of convergence. So we can start by multiplying both sides by 3, and that will give us the inequality absolute value of x minus 2 less than 3. Because we have an absolute value less than inequality, we know that this means that we can set x minus 2 between negative 3 and positive 3. And adding 2 to all parts of the inequality tells us that x is going to lie between negative 1 and 5. So this means that our power series is going to converge for all values of x between negative 1 and 5. It's also worth noting that our center of our power series is equal to 2, and that's actually the center of the interval that starts at negative 1 and goes to 5. And so here we can observe that our radius of convergence is going to be the distance from our center to either of our two endpoints, and the distance from 2 to 5, as well as the distance from 2 to negative 1, is equal to 3. And so here our radius of convergence will be equal to 3. It's also worth noting that we actually could have stated the radius of convergence back here earlier when we had the absolute value of x minus the center less than 3. Recall that in this particular case, our interval of convergence and radius of convergence can be defined by the absolute value of x minus the center being less than this number r, which we found later was the radius of convergence. So as soon as we get a an expression, an inequality in this particular form, we can state the radius of convergence right away, or we can wait until we find the endpoints of our interval and calculate it from that. One important thing to note here is that we're not done. We actually need to check our two endpoints, so x equals -1 and x equals 5, separately. What we know here is that between these two values of x, our series will converge. And we also know by the ratio test that it will diverge when we're bigger than 5 or smaller than -1. But we don't know what happens when x is equal to -1 or x is equal to 5. And so we need to check these two values separately. So let's start by checking x equal to 5. What we're going to do is take our power series, which in this case is the sum from n equals 0 to infinity of x minus 2 to the n over n plus 1 times 3 to the n. And we're going to substitute x equal 5 into our power series for x. And when we do that, what we obtain is the series from n equals 0 to infinity. In the numerator, we have 5 minus 2, which is 3, so 3 to the n, over n plus 1 times 3 to the n. And the 3 to the n is a constant for each value of n, so those will simplify. And we're left with a relatively simple series, n equals 0 to infinity, of 1 over n plus 1. Notice that this is just a standard series. It's not a power series anymore because we've replaced the variable x with a value. And so we want to determine whether this series converges or diverges, and so we can use any of the convergence tests in order to do this. In this case, we notice that 1 over n plus 1 is approximately 1 over n, and we know the series from n equal 1 to infinity of 1 over n will diverge. This is a p series. So this diverges by the p-test, since p is equal to 1. And because these functions are relatively close, and we know that the second one diverges, we can use the limit comparison test here. So we could compute the limit as n approaches infinity of 1 over n plus 1 divided by 1 over n. Which will give us the limit as n approaches infinity of n over n plus 1. And using either L'Hopital's rule or multiplying and dividing numerator and denominator by 1 over n, we see that we get a limiting value of 1 here. And 1 is a non-zero number. And so that tells us that our two series have the same behavior. And therefore, this is telling us that the series n equal to 0 to infinity of 1 over n plus 1, which was our power series with x equal 5 substituted in, this series is going to diverge by the limit comparison test. And so what this is saying is that the value of x equals 5, the right endpoint of our interval of convergence, will not be included because the power series, does not converge at that point. So x equals 5 is not included in our interval of convergence for this particular power series. We now check the same thing with the other endpoint, the left endpoint, x equals -1. If you'd like to try that one on your own, you can pause the video, and the solution for it will be worked out in a few seconds. When we substitute x equal -1 into our power series, we get in the numerator -1 minus 2 to the n, which is -3 to the n. We can write -3 to the n as -1 to the n times 3 to the n, and the 3 to the n's then cancel, and this leaves us with the series from n equals 0 to infinity of -1 to the n over n plus 1. Since we have a -1 to the n in our term for our series, this is an alternating series, and so we can try to apply the alternating series test to determine whether this converges. We let b sub n be the non-zero or the non-negative part of this series, which will be 1 over n plus 1. And we trivially see that that's going to be greater than 0, that 1 over n plus 2 will be less than 1 over n plus 1, so this series will decrease, and that the limit as n goes to infinity of 1 over n plus 1 will equal 0. And since all three of these properties hold, this particular series with x equal negative 1 substituted in will converge by the alternating series test. And this means that x equal negative 1 is included in the interval of convergence. Right? We saw that 5 was not included, and now we see that x equal negative 1 is included. And so our interval of convergence, we already knew, went from negative 1 to 5. We now know that it includes negative 1, and it does not include 5. So we have the interval that is closed on the left from negative 1 to 5, and then open on the right. And we previously remarked as well that our radius of convergence here was 3, the distance from the center of our power series, which is 2, to either of the endpoints, 5 or negative 1. If you'd like to try an entire example like this on your own, pause the video and find the interval and radius of convergence of this series from n equals 0 to infinity of n times x plus 2 to the n over 8 to the n. Resume the video, and in a few seconds, you'll see a full worked out solution for this particular problem. We first note for future reference that the center of our power series is negative 2. This is because the variable term in our power series is x plus 2, and we can rewrite that as x minus negative 2. So here the center is negative 2 as opposed to positive 2. Next, we compute the limit of the ratio of consecutive terms for our power series. Specifically, we want the limit as n approaches infinity of the absolute value of n plus 1 times x plus 2 to the n plus 1, all over 8 to the n plus 1, multiplied by 8 to the n, divided by n times x plus 2 to the n. We can simplify all of the terms here, and we're left with the absolute value of x plus 2 over 8, multiplied by n plus 1 over n. The x plus 2 needs to remain in absolute values, since depending on the value of x plus 2 could be either positive or negative. And the 8, n plus 1, and n will all be positive, so it can be left outside the absolute values. As we take the limit as n goes to infinity, the expression n plus 1 over n will converge to 1, and that leaves us with the value of x plus 2 in absolute value over 8. Since we're using the ratio test here, to determine where the power series will converge, we want to solve the inequality by setting this limit value less than 1. So setting the absolute value of x plus 2 over 8 less than 1, we can multiply by 8 to get the absolute value of x plus 2 less than 8. Split this up as a three-part inequality by putting x plus 2 between negative 8 and 8, and then subtracting 2 to get negative 10 less than x, in turn less than 6. Remember that the center of our power series is equal to negative 2, and therefore our radius of convergence will be the distance from that center to either of the two endpoints, either positive 6 or negative 10. And notice that negative 2 is 8 units from both of those endpoints, and so we get a radius of convergence equal to 8. We also know the interval of convergence is going to be from negative 10 to 6. We just need to determine whether those two values are part of the interval or not, and in order to do that, we need to check the values of x equal negative 10 and x equals 6 separately in our power series. When we substitute the left endpoint, x equal negative 10, into our power series, we obtain the series from n equals 0 to infinity of n times negative 8 to the n over 8 to the n. We can break up negative 8 to the n as negative 1 to the n times 8 to the n. The 8 to the n's cancel, leaving us with the series from n equals 0 to infinity of n times negative 1 to the n. Because the limit of n as n goes to infinity of negative 1 to the n times n does not exist, which we can see by realizing that n is going to get extremely large, and the negative 1 to the n just alternates signs, and so our terms of our sequence of terms will just simply be getting closer and closer to positive infinity and negative infinity, respectively. This limit does not exist, and therefore it's not equal to 0, and so we have a series that diverges by the divergence test. And so x equal negative 10 is not included in our interval of convergence. When substituting x equals 6 into our power series, we obtain the series from n equals 0 to infinity of n times 8 to the n over 8 to the n, which is just the series from n equals 0 to infinity of n. Since the limit as n goes to infinity of n is positive infinity and not equal to 0, this series also diverges by the divergence test, and the right endpoint 6 is not included in the interval of convergence either. Since neither endpoint is included, our interval of convergence is the open interval from negative 10 to 6, open on both the right and the left, not including negative 10 or 6, and our radius of convergence, as mentioned earlier, is equal to 8.